Hi. Um, do you remember anything from the last episode? Because I sure hope you do. It would be really helpful for you today. This is lesson 86. I'm going to talk about two kind of applications of geometric stuff, Pythagorean, whatnot. That's going to be midpoints and distances. We're going to be living in the geometry world, but we're going to kind of like bring our geometry garbage over into the realm of algebra and what's called coordinate geometry. So let's philosophize for a minute. The Greeks used to think of all their shapes, circles and triangles and squares and whatnot, as being these ideas. Okay, there's a perfect square and a perfect circle up in heaven, but here on earth we really can't represent it exactly. I mean, if you've ever tried to draw a circle by hand, you know how lame that is, or draw a straight line or anything like that. So that for them, these objects are these kind of floaty things. We can kind of put them wherever and think about them, but as soon as we put them on paper or a papyrus or on a sand table or something, now we're off by a little bit, and our picture is just an estimation of the real thing. Okay, well, at a certain point, 1600s, 1500s, whatever, there's this guy named Pierre from, no, Rene Descartes. There we go. Rene Descartes, philosopher, mathematician, whatnot. He says, why can't we take those weird shapes that we can't draw and let's put them on my new grid coordinate system? We got an X and a Y axis, and everything turns into these squares. We can like identify where something is in the plane by giving it an address, right? So you take your old clunky square, you take your old clunky triangle, and you attach it into a brand new system. And again, this is like the merging of algebra and geometry, coordinate geometry. Brand new thing. Let's take geometry with all its just, we're not really measuring any distances. We're just kind of drawing the pictures and stuff. And let's plunk it onto a grid where it's like set, it's firm. We can do stuff with it. So there you go. We've plunked it down there. Now we've got addresses. We can take something like a triangle, and we'll say that's a 90-degree angle there because this is coordinate geometry. Everything's 90 degrees from each other. I can say now what the address is for. Oh, what is this? This is 70. We can say exactly where that thing is in space on a plane. And we can apply the same things we were doing with just the triangle shape from our last episode and make it algebratized. Okay, so I can apply my c squared is a squared plus b squared thing to algebra. I can now think of it in terms of just doing the math, but I can see a picture that goes along with it, and the two match each other. That's pretty nice. One thing that we were working with, and I'm going to cover the distance thing first, and then we'll get to midpoint. One thing we can see now is that we can, no longer is this just like how long is the side. Now we can kind of think of it as terms of how far do I have to go. Like instead of saying length, thinking about lengths, we can think about distances. I know that doesn't sound too different, but if you just got a triangle and you're like, wow, that's a neat triangle. I wonder how long each side is. And then you plunk it down in the real world and you say, how far is it to that other point over there? It's the same idea, but just a little twist to make it applicable in a new way. So you're building stuff, you're cutting paper, you're trying to build a track out there in the field. You want to make sure that everything's straight. And you're going to use coordinate geometry. You're going to want to check distances and midpoints and lengths and all that kind of stuff. So we got some place out here at 7,5, and we want to get there. And if we're in a coordinate system, we got two ways to get there. We can go in just straight lines, like a street system that's all on a big grid, or we can go from point A to point B. Okay? I could even call them point A and point B, and we got this intermediate place here, C, where we could travel there first and then go to B, the thing that makes going from A to B hard is we don't really have a good way of saying exactly how far that is if we're in the coordinate system. We have a really easy way of finding how far that is if we go from A to C first and then from C to B, because we can measure the length of that side, or we can figure out the distance from 0, 0 to 7, 0. I'm going to call that a change in the x variable. And it went from 0 to 7, so we know that this is of length 7, or a distance of 7 units. And we have a good way of going from 7, 0 up to 7, 5. Because we're going in a straight line in the y direction, we can say, well, we go from 0 here up to 5 there. This must be a distance of 5. So we could say we've got, if we went A to C and then C to B, we have to go 7 plus 5 is 12. But that's not the shortest distance, is it? We'd like to go the shortest distance. If we use Pythagoras there, and I'm going to call this delta y, we would have to figure out how far that is and square it, how far this is and square it, and that'll give us that distance from A to B, but we'd have to square that, take the square root of it. So what I'm going to do is I'm just going to solve for this thing over here from that distance from A to B. I'm going to just solve for it right now by taking the square root of both sides. Okay, so that length A to B is equal to how far I had to go, how far I had to go in that x direction and how far I had to go in that y direction squared, and I'm going to take the square root. And that, my friends, right there is what's called the distance formula. We're looking for the distance from A to B as being how far that x changed and how far that y changed, and we took the square root of it. Now, it's a little bit different than what maybe you see in your book, but I'm just thinking about the difference between those 2 points A and C as being the distance that you have to go. The difference is the distance. The difference in the x variables is how far you had to go. The difference in the y variables is how far you had to go. Okay? So they call this the distance formula. It is basically the Pythagorean theorem just dressed up. So let's imagine we got a big old field here, and we got this kind of problem. What about this, what they call the diagonal there? How far is that? Well, we've got a way of figuring that out. This turns it into 90-degree triangle rather than this kind of grid. I don't have to care about this part. It's the exact same thing as this part. And I got 3 squared and 4 squared equals my Pythagorean triplet of 5 squared. But what if I want to find out this distance, where now I'm only going, well, I guess that's 3 this way and 3 that way. This isn't going to be a nice clean answer, right? It's going to be 3 squared and 3 squared. 9 and 9 makes 18. It's the square root of 18. Or if I want to clean that up a little bit, 2 times the square root of 3 is the distance. But I got a way of doing that now. I've got the distance from this point to this point would be, well, how far did I go in the x direction? I have to go out 3. How far do I go in the y direction? I'm also going 3. In this case, I'm going down 3. That's okay. I'm going to square it, where I'm going to get my distance. So I've got a change of 9, and I've got a change of another 9 that equaled that square root of 18, or 2 square root 3. Distance is just going to be the difference if we're on the coordinate grid of how far to go in the x direction, how far to go in the y direction, and then we can finish it off. Another interesting question is, how far is it to if I only want to go halfway? Well, not necessarily how far do I have to go. That's an easy problem. Just divide by 2 whatever our distance is. But where am I when I'm halfway? And I'll take this one here, and I'll say, you know, somewhere in there is what we'll call the midpoint. I want to know what its address is if perhaps I plunk this onto a coordinate grid, and this is my y, and this is my x-axis. I'm going to turn this into a, there's my problem. there. What's that address for this point in the middle? I'm going to take a second to breathe and finish this up. Yeah, I have a feeling this is going to be a two-parter. I really want to hit this distance thing for you. Hi, I'm right here. Do it this way. I was kind of explaining that this distance formula thing is like in the coordinate plane now, and sometimes we want to tether things to 0, 0 to make it easier, but we're also going to do this just wherever. We want to find the distance between 2 points. The book uses this formula right here, and you probably should write it down, but I want you to think of it more conceptually as how much does the x change and the y change. We can turn whatever problem we want to in the coordinate plane into just a geometry picture and just count rather than calculate. I think sometimes when people put their numbers into the formula, they get all put the numbers in the wrong place and they think, well, which one's the first one and which one's the second one, and it does matter. But I think if we just turn this into a picture, it'll be easier to not make mistakes. So the first question is, how far is it out to that point? This point is out at 1, 2, 3, 4, 5, and up to 1, 2, 3, 4, 5, 6, 7, 8. So it's at the point 5, 8. There's no simple way to do that except turn this into a triangle problem. So that's what I'm going to do. I'm going to turn this into a triangle where that's 5 and that's 8, and because it's in the coordinate system, that's a 90-degree angle. And we've got how far did the x change? 5. How far did the y change? 8. We can turn this into the square root of 5 squared and 8 squared being the distance. And that's just calculations, right? 25 and 64. It's like 89, right? Prime number. That's our distance right there. That's not so bad, right? That's just an application of the Pythagorean theorem. Let's take it one step further and we say, what if 0, 0 is not one of our points? And we get the points -3, -3, and -2, 6, which I randomly generated. I want to turn it into a triangle. I've got grid paper, so why don't I do that? I'm going to have to go over 1. I'm going to have to go up, and I'm just going to count it. So that there is a distance of 1. And this there is a distance of 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and I want to go from here to there, but I'm going to use that other path to get there. And I'd have to use the distance formula that I cooked up, that the change in that x value was 1. I'm going to square it. And the change in the y value was 9. I don't care where they are anymore. I've already got all the information that I want to. So what do we got? 1 squared is 1, and 9 squared is 81. I've got the square root of 82, or I better probably clean that up a little bit. Nope, that's it. I can't clean it up, can I? Be 41, which is prime. There you go. There's our distance right there. So coordinate system is really good for these types of problems. I don't need to know a whole lot of information. I can just draw the picture and use my intuition. I can use my brain to figure out how far it changed in the x direction and how far it changed in the y. If I'd like to do the whole formula thing, then maybe I'd do something like -2 minus -3 squared and 6 minus -3 squared. And the problem with that for me is that there's all these negatives, and do I square it first and then subtract? And it just really gets sloppy, whereby the picture was a lot faster. So that's my suggestion. Draw the picture. Know that that formula does work, but it's a lot easier if you can just see it and count the spaces that you have to go. Again, 1 is the change in the x, and 9 is the change in the y. And then I can just use my little distance formula right there for figuring out the missing parts. Okay, I'll get back to you on that midpoint thing here. That one will be shorter. Give me like 6, 7 minutes, and I'll be on that. Thanks.